So classification is the class of algorithms within supervised learning where your dependent variable is a categorical variable. So a categorical variable would be something like result, which would say pass or fail, or an answer, which could be yes or no. Now, to solve the class of problems, which is classification, we have a simple technique called logistic regression, which is widely used and very popular. Now, logistic regression is a technique that determines the relationship between a dependent variable and one or more independent variables, where the dependent variable is a dichotomous categorical variable. Now, dichotomous categorical variable is a categorical variable where you have only two outcomes at max. So something like, let's say, yes or no. That would be two classes, yes and no. So that's a dichotomous categorical variable or a binary variable. If you have three values, let's say yes, no, maybe, that wouldn't be termed as a dichotomous categorical variable, and we wouldn't be able to use logistic regression to solve such a problem. Now, since it's based on the definition of regression, where you say it's a technique that determines the relationship between a dependent and one or more independent variables, it sounds familiar with linear regression. So we kind of assume that we represent the categorical variable on the y-axis, we draw a line which determines the relationship between these two, and leverage this equation to find out the unknown y when you know an x, right? But then it's not really so straightforward. Let's look into a visual example and understand this better. So if you remember from the linear regression equation, we would say we have a y and an x, and both of them are numeric. So you define a simple line as the relationship between them. You can find for the corresponding x what is the corresponding y, and you find this value. This would be the y for that corresponding x, right? It is a very straightforward process when we have this, if we have the equation on this line, which is y is equal to mx plus c. But then when your y is categorical, right, which means it can take values, let's say, like pass or fail, how does it really work? Can we put pass and fail into this equation? Not really possible, right? So what could be a workaround over here? Do we really have an alternative that we can encode this into the y-axis? The easiest one, which sounds simple, would be converting them to a numeric format. So you say pass is 0, 1 is fail. And on your y-axis, you'll say this is 0, this is 1, anything beyond 0.5 is 1, anything below 0.5 is 0. But then if you define an equation like this, the core problem is you're saying pass is less than fail, or fail is greater than pass, which is not the case, right? You can't really determine them using numbers where it will be encoded as fail has a greater value than pass. The algorithm won't learn this correctly. It will be interpreted in an incorrect way. So what is an alternative where we don't lose all this information? Now, an easy alternative which we have in front of us is using the log of odds. So log of odds in simple terms can be determined as the log of the probability of an event happening divided by the probability of an event not happening, right? So it could be any positive finite number. So let's say you have yes as the probability of yes as, let's say, 0.4, and the probability of no as 0.6, which is 1 minus 0.4. Now if you put this in the equation, we'll say it is 0.6 divided by 0.4, and you have a finite positive number, right? So if you plug this into this equation, you'll say that, okay, y can be determined as a simple finite number, which is between, let's say, 0 and some finite number, right? Let's put it as n. And then we have x over here, which could be your number of r's. So you kind of solve the problem of categorical variables. But then still we are not complete. Now, how do you determine a cutoff over here? Like, can you say confidently that this will be cutoff, and beyond this we say, okay, it is yes, and below this it will be no. Determining this cutoff is not a straightforward thing. So we simplify this by converting into probability. Now, this can be done using the logit function. Now, the logit function is used in logistic regression to convert the log of odds into a logistic equation so that you can get the respective probability for a respective event. It may sound a little complicated, but then let's use the simple math to understand this. So initially we would say y is equal to mx plus c was the equation which we have for linear regression. Now we convert this to a more optimized format where we would say log of odds is a log of p upon 1 minus p is equal to mx plus c, right? Now, to decode this further, we need to convert this into a format where we have the logistic function so that the output can be delivered in terms of a probability value which can be between 0 and 1. So if you solve this further, if you take exponential on both the sides, we would get p upon 1 minus p is equal to e raised to mx plus c. Now we can simplify this further. What we can do is we solve this further by saying p upon e raised to mx plus c is equal to 1 minus p. If you take it further, we would say p plus p upon e raised to mx plus c plus p is equal to 1. Now take out p common, then we say 1 plus e raised to mx plus c upon e raised to mx plus c is equal to 1. And if you reverse the equation, I know I'm going a little long way, I would say p is determined as e raised to mx plus c upon 1 plus e raised to mx plus c. So you have a probability value over here, right? So using this, you can actually get an outcome for probability value that you would say for a function, let's say for a function where you'd say the value would be between 0 and 1. So you're technically converting the log of odds over here into a logistic function where you get the output in terms of 0 and 1. Sorry for the tilted output. I have a bad habit of writing in a with the iPad in a different way. So that's why you got the output in a tilted format. But then you get the idea. So that's what we have over here. We have, let's come back over here. Now we have a simple equation where we say the logistic function is leveraged to convert the probability of an event, to convert the log of odds into the probability of an event, where you get the values between 0 and 1. So your equation is determined, right? So we solve the first part of the problem, that is, we represent the problem. Now the next thing is we need to define the cost function, right? So in linear regression, we had a fairly straightforward cost function. You had a y, you predict another y, you need to find out the difference between them. So we kind of represented earlier using simple percentage error, but then a more better means in that scenario would have been percentage square error, or sorry, RMSE, root mean square error. The moment you square the errors, so bigger errors will be amplified so that the algorithm learns and it gets penalized so that it can learn for downgrading that value. But in this scenario, we need to build the cost function in terms of the log of odds. So you say the cost would be minus log of h of x. H of x over here would be the log of x when y is equal to 1. And then minus log 1 minus h of x when y is equal to 0. The combination of that, you can say, the combination of cost function for the parameters can be defined as from I to n, summation of I to n, yi log of h of x. You just convert this into a cost function. So you say yi log of h of x of I plus 1 minus yi log of 1 minus h of x of I. So this determines the cost function. Now when you optimize this, you actually optimize using a gradient function. You optimize this function and you find out the optimal parameter values that will go into the equation. So we'll have parameter values for A and B. Now the optimization is done by basically maximizing or minimizing a function. Now to do this, we differentiate the function and find the point where the gradient is 0. Now since this is a nonlinear function, we use the gradient descent. That is, we calculate the gradient of the function at a point we want to optimize, and then we move in the direction of a negative descent. And that is, we update the value. So how does it happen? Just assume that for simplicity, you are representing, let's say we have a simple curve, right? And you are right now over here. Just assume that you're standing on top on a valley of a mountain, and this is the point where you're right now, and this is where you need to go. So you first calculate the gradient over here. at this point, and negative direction. If you understand that this is the direction, that this is the negative direction you need to go, you'll eventually come to a point where you'll get the lowest value. Now, once you have the lowest value, you understand that this is probably the most optimal value. Now, this is an oversimplified version of calculating the gradient descent. You take a derivative at this point, you calculate the direction you need to move ahead, and you gradually move down, you reduce the gradient, and when you find the value, it is the most optimum value. So that algorithm is a detailed algorithm which needs more explanation and more math. For now, we'll just keep it simple. We can simplify this that we have a non-linear function and we use a gradient descent algorithm to calculate the gradient of the function at each point we want to optimize. And we move in the direction of the negative descent. And eventually, we reach the most optimum point. And then finally, we reach that, when we reach the most optimum point, we finalize that as the values for the parameters. And at each step, you update the values of the parameter. So that's, in a nutshell, supervised learning algorithms for classification. Right? I mean, classification is under supervised learning algorithm. So we have learned logistic regression. How does it function? How is it different from linear regression? And we understood basic math about how is the probability calculated and what is the background optimization function and the cost function. Let's look at a simple demonstration where we can understand this using a Python code.